Hello, everybody. Uh, there's one extra thing that I haven't brought up yet. Um, when we were talking about light and spectra, I alluded, I think, to how you can use the spectra of stars to figure out their motion, but I didn't really get into it when we were doing spectroscopy because I'm talking about it here. Uh, when you look at the stars in the night sky, they don't really look like they're moving, do they? Right? You look at the stars, you watch them, right? I mean, they move across our sky, they move overhead, rising in the east, setting in the west, but that's not really caused by the motion of the stars, is it? That's caused by the motion of the Earth. But the stars really are moving through space, right? Everything in the universe is in motion. All of the stars in the galaxy are all moving around the galaxy, and the sun is moving around the galaxy. So, from our point of view, here on Earth, relative to the Earth, relative to the Sun, all the stars are in motion. But when you look at the stars, you go and look at the stars of month after month, year after year. They don't really look like they're moving, do they? They look like they're more or less in the same positions. Why is that? Why do the stars look like they're standing still? And the answer is because they're really far away, right? A star could be moving through space at a pretty fast clip, and yet when the star is so far away, it's just going to look like it's standing still, right? So, how do we figure out the motion of stars? How do we figure out which ones are moving fast and which ones are moving slow if they all look like they're standing still? Well, there's a couple of ways to do that. Because there are a couple of kinds of velocity, right? If a star is moving in some direction through real space out there in the galaxy, you can break this velocity down into two separate kinds of velocity. Now, okay, remember, what do I mean by velocity? Right? We talked about this. Velocity is what? Velocity is the speed of an object plus the direction, right? Velocity doesn't just mean how fast something's moving, it also means what direction it's traveling in. So if a star is traveling in this direction with some speed, right, it's got some velocity off in this direction, we can break this velocity up into two components. How it's moving radially toward or away from us. So when I say radial velocity, what I mean is how fast is it moving toward or away from our solar system. And then the transverse velocity, which is how fast is it moving perpendicular to our line of sight. How fast is it moving in right ascension and declination? How fast is it moving east, north, south, east, or west around the celestial sphere? Right? That's real three-dimensional velocity. It can either move perpendicular to our line of sight or along our line of sight toward the Earth or away from the Earth. Well, how do we measure the transverse velocity? Well, that's hard. Because if a star is really far away, then that star will move, from here, let's say, that star moves from here to here, and we can watch it move this distance because that star moved a certain angle uh, across the night sky. It moved through a certain angle on the celestial sphere. It moved through some angle in right ascension and declination. But because these stars are so far away, the proper motion is tiny. So proper motion is a speed, it's a velocity, right? Proper motion is what angle did that star move through per second or per year or per 100 years. And honestly, you tend to measure the proper motion in very, very, very slow speeds. Uh, Look at here. Here's a series of pictures of the star 61 Cygni. Right? Now, we've talked about 61 Cygni before, so if you remember, 61 Cygni is a really nearby star. It is one of the closest. It's only about 11 light years away. 61 Cygni was the very first star whose parallax was measured. That's how close it is. It's got one of the highest parallaxes. And if you watch this star, notice the timestamp down here. This is a series of images going from 2012 to 2020. So these pictures span 8 years. And in 8 years, this star, one of the closest ones, moved just that far. Right? Now this scale bar here is about 1 arc minute, or this scale bar here is 1 arc minute. So these two stars, 61 Cygni is a binary system, these two stars moved not even an arc minute over 8 years. And this is fast compared to other stars, right? Other stars have these tiny little proper motions. You measure these tiny little angles of motion across the sky in decades, right? So measuring the transverse velocity, measuring how this star moves relative to the background stars. How do these stars move north, south, east, and west on the celestial sphere? Takes years of time and very careful measurements. It is painstaking work. So that's the tough part. The easy thing, though, is that the other component of velocity, the radial velocity, is actually really easy to do. And that's where spectra come in. Because light is a wave, right? And all waves have this property called the Doppler effect. So let's talk about sound waves for a second here, right? Let's imagine you're standing along a railroad track, and there's a train going by, and that train blows its whistle, right? If the train's not moving, then the train whistle sounds like normal. But if you're standing there along the railroad tracks and the train is traveling away from you, then because the train is traveling away from you and it's giving off these sound waves, those sound waves are being stretched as the train moves away from you. The sound waves are being stretched to longer wavelengths. And now, how do we, well, remember, longer wavelength means lower frequency, right? And how do we experience different frequencies of sound waves? Well, that's what we call pitch, right? So the pitch of a sound is its frequency. So if you are standing along a railroad track and that train is blowing its whistle traveling away from you, then the sound of the train whistle is pitched down to a lower pitch, a lower frequency, a longer wavelength. All right. Now let's say, for example, you're actually standing over here and the train is traveling toward you. Well, as that train blows its whistle, because the sound waves are traveling toward you and the train is traveling toward you, those sound waves are being squeezed. They're being compressed to shorter wavelengths, and shorter wavelength is higher frequency, and therefore the sound that you hear going in your ear is higher pitch. So we experience this all the time, right? You're standing on the sidewalk and a car drives by you. When a car drives by you real fast, when it's traveling toward you, the engine noise gets pitched up to a higher pitch. And then as soon as the car drives past you, now all of a sudden the car is traveling away from you and the engine noise is lower pitch. And there's that quick little transition from pitched up to pitched down. Because right as the car is traveling past you, it's traveling toward you and then away from you. Right? Well, the Doppler effect happens with all kinds of waves, including light waves. So if you take the spectrum of a star, let's say, we're going to call this the laboratory spectrum, right? This is the spectrum of the star that we see in a lab, and because it's just sitting there in the lab, if you could put a star in a lab, because the star is in the lab, oh, it's not moving. I can control the motion of the star, it's not moving, and you'd say, okay, here's the absorption spectrum of that star, and here are the normal absorption lines from the star's spectrum. But if that star all of a sudden is now receding away from us, if it's traveling away from us, then just like if the train is traveling away from us, those light waves are getting stretched to longer wavelengths, and longer wavelength light is redder light. So all of these colors of the spectrum are being stretched to longer, redder wavelengths. So instead of those lines, instead of those absorption lines happening over here in the yellow, that yellow light is being stretched to look like red light. And so what you see here on Earth is that because that star is traveling away from us, that same pattern of absorption lines is now in the red. Oops, pardon me. On the other hand, if the star is traveling toward you, well, then it's like the train traveling toward you. Those same colors are now being squeezed, compressed to shorter, bluer wavelengths. And therefore, instead of seeing those absorption lines in the yellow, you now see them in the blue, right? So this is what we call, in astronomer shorthand, we say if the star is traveling away from us, its light is red shifted, meaning the entire spectrum is shifted toward the red end. And if the star is traveling toward us, then the spectrum is blue shifted. The whole spectrum, the light and the dark absorption lines and all of it, is shifted toward the blue end of the spectrum. And the faster the star is traveling toward us, the greater the extent of the blue shift. The faster the star is traveling away from us, the greater the extent of the red shift. And this is easy to do, right? That transverse velocity takes years to measure. The radial velocity is a piece of cake. Because if the star is traveling away from us or toward us, all you've got to do is take the spectrum of the star. Look at the spectrum of the star and see, is it standing still? Or is the spectrum red shifted? Is the spectrum blue shifted? You can take the spectrum of a star in a few minutes and boom, you know if it's traveling toward us or away from us. So the Doppler effect is a really powerful tool in astronomy, not only because it tells us how fast the star is moving. Granted, it's only telling us how fast the star is moving toward us or away from us, but hey, better than nothing, right? But also it doesn't depend on distance, right? The Doppler effect only depends on how fast the star is moving toward us or away from us. It doesn't depend on how far away the star is. If you can get the light from that star, look at its spectrum, and see if the spectrum is shifted toward the blue or toward the red, boom, you've got the radial velocity immediately. So let's look at this in reality here. Let's look at a little more realistic situation, right? Here's the spectrum in our stationary spectrum, right? The stationary spectrum, a star that's not moving. Here are the typical hydrogen absorption lines, right? There's that red hydrogen absorption line. And, if you're going to measure the velocity of a star, use the hydrogen lines because it's a star. It's always going to have dark, obvious hydrogen absorption lines. And so you say, okay, well, there's the spectrum at rest. If you see a star, if that line is right where it is for all hydrogen, right? If hydrogen at rest absorbs light right there, and that's where you see your star, then you know, that star is not moving toward me or away from me. That star is at rest. But if that same hydrogen line, and if the entire spectrum is shifted toward the red, then you know the star is moving away from you. That spectrum is red shifted. If the whole spectrum is shifted to shorter wavelengths, bluer wavelengths, then you go, aha, that star's light is blue shifted, the star must be traveling toward us. Right? So you can tell instantly if the star is traveling toward you, away from you, or neither. Right? But, okay, so that's a good thing. But let's do you one better. How fast is the star moving? Right? For that, we need to actually measure the wavelengths of those lines because the velocity, the radial velocity of that star can be measured by taking the rest wavelength of that line, right? So Hydrogen always absorbs light at that wavelength, and so you take the rest wavelength, meaning the wavelength that hydrogen absorbs that light when hydrogen's at rest. And then you measure, okay, but what is the wavelength of that line for the object I'm looking at? For the star, or the nebula, or the galaxy, or the whatever. Let's assume that the object I'm looking at is a star, right? So then I say, well, if this is the spectrum of the star that I get, I say, well, that's that hydrogen absorption line, but it's not at the usual wavelength over here. I'm actually measuring it over here. The spectrum has been shifted, in this case, redshifted, right? So you take the object wavelength, you take the wavelength of that line for the object that you're looking at, and then compare it to the wavelength of that line when the star is at rest, and that can give us the velocity, right? You take the object wavelength minus the rest wavelength divided by the rest wavelength times c, the speed of light. And that gives us the speed of the star, right? So now let's take an example, right? All you got to do is let's just use that same hydrogen absorption line, because it's going to be there for all the stars. The only thing you need to measure, the only new thing you need to measure is what is the wavelength of that same line for your object. Plug it in, boom, you've got the velocity of that star. Okay, let's see an example here, right? Let's say you look at a star and you look at the spectrum and you go, well, those are the hydrogen lines, same as always, but they've been shifted. So let's measure. Let's say that my star has that same hydrogen line, except now it's at a wavelength of 660.0 nanometers. And you go, okay, but what is the wavelength of that hydrogen line at rest? Well, the wavelength of that line at rest is 656.3 nanometers. And so you say, well then, 660 minus 656.3 divided by 656.3 times the speed of light, right? And the speed of light is 3 times 10 to the 5 kilometers per second. You plug all of these in here, and it turns out that star is moving with a velocity of 1,691 kilometers per second, which is pretty darn fast, right? It doesn't tell us anything about how fast the star is moving transversely, right? We don't know how fast it's moving east, west, north, south. But we know immediately it's moving radially at 1,691 kilometers per second. And is it moving that fast toward us or away from us? Well, because the spectrum is redshifted, because that line is at a longer wavelength, that means the star is moving with a velocity of 1,691 kilometers per second away from us. Right? If the star were moving toward us, then the object wavelength would be shorter than the rest frame wavelength, and when you subtract them, you'd get a negative number. This is very important. Always do the object wavelength minus the rest wavelength, because if you subtract them and you get a negative number, then you're going to get a negative velocity. What does that negative velocity mean? It tells you the direction. Negative velocity means it's traveling toward us. Positive velocity means it's traveling away from us. So there you go, right? We can measure the proper motion, right, to go back, right? We can measure the proper motion of these stars by watching the stars for years and years, and the proper motion can tell us the transverse velocity. Takes a lot of work, but we can do it. Radial velocity is a piece of cake. You can get it in a single night just by using the Doppler effect. Right? So that's why radial velocity and the Doppler effect is such a powerful tool in astronomy, is because it's a way of figuring out something fundamental about these stars. How are they moving through space? Ideally, you want both velocities, so that you can add them together to say, well, what's the real space velocity of that star? If you've got that information about the star, fantastic. You know its real velocity. If you can't get the transverse velocity, though, at least you got the radial velocity really quickly and effectively. And this is how we measure the velocities of objects as they move through the universe.